And thanks. Since my talk time is now over, I'm happy to take any questions. I'm really, really happy to be able to talk today about effect handlers for the masters, which is joint work with Philipp Schuster and Klaus Ostermann. And in fact, I presented a Scala library for working with effect handlers last year at Splash, and it's a monadic library. And after my presentation, people approached me and said, hey, your library looks really cool, but I would like to use it in Java, and if it's possible, I would also not need to write everything in monadic style, because monadic style is really difficult to sell to Java programmers. So I went back to the drawing board and redesigned the whole library to make it fit in the Java ecosystem and with the Java programming paradigms. And now 1 year later, I'm happy to present to you the new design of the library for Java, and hence for the masters, because the target audience for Java is a bit bigger than Scala. In particular, in this talk, I first want to show you, introduce effect handlers to you, and at the same time also show you the most important design decisions, and to then dive a little bit into the implementation details. And finally, I want to illustrate how combining object-oriented programming with effect handlers emerges new modularization and extensibility opportunities. But first, let's talk about effect handlers and what are effect handlers. So effect handlers have a deep theoretical foundation in category theory, but today, for the purpose of this talk, it's enough to understand them as a new way to structure your programs. In particular, you split that, when working with this programming paradigm, we split the programs into 3 parts. We have effect signatures, which kind of group available effect operations. And then we have effectful programs that use these effect operations. And we have effect handlers that give semantics to the effect operation. And the effect operations otherwise are abstract, and only effect handlers give semantics to them. Okay. Another way of talking about effect handlers is seeing them as a structured way for programming with delimited continuations. So you're probably familiar with that if, for, and while are structured ways to program with local jumps go to. And effect handlers can, in the same way, be seen as a structured way to program with delimited continuations, like shift reset and other constructs for control flow. While being more structured, they're still very expressive. And for instance, they can express many control flow paradigms like async await, fibers, cooperative multitasking. But all of that as a library instead of building in these features in your language. At the same time, they simplify typing compared to typing of general delimited continuation. Effect handlers are not new. So the contributions of the work that I present today is a first library design to program with effect handlers in Java. And one major problem we had to face there was we had to simplify the typing discipline. And our library design only requires simple generics. And in particular, the implementation is based on an implementation of multi-prompt delimited continuations, which in turn we perform via some bytecode transformation. I go into some details later, but a distinguishing feature of this bytecode transformation is that it uses Java 8 closures and invoke dynamic. So enough of the high-level description. Let's just look at an example. And this is a very academic example. It's a drunk flipping a coin. It's often used in the effect handlers literature. And in particular, you see here 3 different effect operations. So we see 2 flip operations and 1 raise operation. And we first flip the coin to determine whether we dropped it. And if we dropped it, we raise an exception. If not, we flip it again to see whether it's heads or tails. Okay? So these are called effect operations. And they are called on capabilities. So the method signature shows that it uses these 2 effects, an ambiguity effect and an exception effect. And it also mentions this special exception, which we use to annotate that the method actually has any kind of effects. So now the two capabilities, they have this type which is defined in these interfaces, and these we call Effekt signatures, as we already have seen in the overview. And Effekt signatures just declare and group the Effekt operations. For instance, the ambiguity signature here mentions the flip Effekt operation, which returns a Boolean. So now handlers are just implementations, just classes implementing these interfaces. Okay? For instance, we could use native Java side effects, and for instance, with the exception effect, we could just throw a Java exception. And for the random implementation, we could just use math.random to get a random number. But with Effekt handlers, we get a superpower. We can do much more than just these standard Java implementation here. Oh, this is how we would obviously call this function, right? So with Effekt handlers, now we extend our library interface, which is called handler here, and notice that it has two type parameters. Typically, when a program would return something of type R, now the handler is able to transform this into, for the maybe case, optional R, and for this collect implementation, list of R. Okay. And on the left-hand side, we see the original result type. The right-hand side, we call the Effekt domain. So now for a particular call of our drunk flip example, which would typically return a string, if we now first handle it with the maybe handler, it translates the result type of string now into an optional string. And if we then handle it with the collect handler, it translates it into a list of optional strings, yielding this result. So we have a list with optional heads, optional tails, and optional empty for the exceptional control path. The nice thing about Effekt handlers is that it's very, very easy to change the semantics by swapping these two handlers. So now we first handle the ambiguity effect, and then we handle the exception effect. And the types already tell us it's different. We now have optional list of strings. And also the semantics changes. Now, since there's one control path which has an exception, we get an overall optional empty result. That's only because we swapped these two handlers. Also note that here, exe and amp, these are capabilities which are introduced by our corresponding calls to handle. And users have to follow a capability passing style where they pass these capabilities to the corresponding functions using them. For a concrete implementation of this collect handler, we again extend our handler interface here, which goes from R to a list of R. And since we extend this interface, we need to implement two different things. One, we need to implement this method pure. Pure translates a program which does not have any further effects into the Effekt domain. So here, the pure result R will be wrapped into the singleton list. And of course, we also need to implement our Effekt operations, which in this case is flip. And now comes the superpower that handlers give us. We can now capture the delimited continuation, which is bound to K here, and invoke it twice. So once we try it with true to get a list of potential results, we call it again with false to get a list, then we concatenate the list to enumerate all possible results that we could have. So for this particular example here, the delimited continuation corresponds to this marked region here. In particular, it does not extend over the other handler, only until the next handler corresponding to this ambiguity effect. And now calling the continuation is just substituting true here, doing some reduction, and in the end also evaluating our pure method to get a singleton list with just the entry heads. We would get the same thing for false, but just with the entry tails, and then concatenate it to the list heads and tails, which is all possible results for this simple example. So to summarize the design decisions, Effekt signatures just correspond to Java interfaces. There's nothing really special about that. And Effekt for programs are just Java methods, the only twist is that they use these capabilities to perform control effects, and they are marked with this throws effects exception. And effect handlers now are just Java classes, but if they extend this handler interface, they have this power of capturing the delimited continuation, which is, can be used to express many, many different control flow paradigms. In the second part now, I want to talk a little bit about the implementation details of how we managed to acquire the delimited continuation. And this is a very high-level overview of the framework. As we have seen, we just write direct-style Java programs, and you would compile these Java programs to bytecode. And what we provide you with is a bytecode transformation. The translated programs, the bytecode transformation is basically a CPS transformation. The translated programs now make use of a separate stack interface, not using the original JVM stack, but a separate stack where we have more control over. And then using this stack interface, we implement delimited control, that is delimited continuation support, and the library itself is based on top of this layer. So many of these components can also just be reused. If you don't want to program with effect handlers, but only with delimited continuations, you can reuse at least the left half of the framework. One important restriction is that our translation, the CPS translation, preserves signatures. So typically, you would change the signature to reflect that it's now CPS translated. We don't do that to allow separate compilation and backwards compatibility with other Java features. So this is an important restriction and shows in several design decisions in the implementation. As I mentioned, we not use the JVM stack exclusively anymore, but in addition, for pure methods, we use the JVM stack, but for effectful methods, we now have our own stack, which I call here Effekt stack, and we have now more control over the stack. For instance, if we use a handler, we introduce markers on this stack, and then we can implement like searching for these markers, slicing parts of the stack, and later copying it when we resume. So we have now full control over the stack. The CPS translation itself is a transformation of bytecode, as I mentioned earlier, and it uses the stack interface to push the current frame before we enter an effect operation. But it also uses the special calling convention, which we see in a second, to allow us preserving the signatures, not having to change the type to reflect that it's a CPS transform. And in particular, for our example here, this means that we generate 3 different functions. This is called the initial entry point here, and 2 others, which are the continuations after respective effect calls. And before we actually perform the very first effect operation, we now have to remember where we left off. So we push our continuation to our separate effect stack and remember all local variables, like amp and exe here, these capabilities. And in our bytecode transformation, so this is source to source to make it easier for the talk, but in our bytecode transformation, this amounts to storing all operands and all locals register contents, but closing over them using Java 8 closures. Then when we resume, we get the result also using our special calling convention here. And again, before we call the next operation, flip in this case, we store the current state of our function by pushing this frame that closes over all register contents and operands, so that later we can resume it. In the end, we get the result, and again, instead of actually returning from the Java method, we now use our special calling convention to return from this Java method. So finally, I want to show you another example that illustrates a bit of how combining effect handlers with object-oriented programming gives us a new potential for reuse and modularity. And as we have seen, effect signatures are just represented as interfaces, and this has a number of consequences. So we can just use now Java object-oriented programming, which means we can mix signatures to the desired granularity that we want. One handler can at once implement multiple effect signatures, and thereby also share this effect domain, the knowledge of the effect domain that otherwise might be encapsulated. And obviously, also, one signature can be implemented by different handlers, because the Java interface can be implemented by different classes, right? So that's obvious at that point. At the same time, interface subtyping gives us effect subtyping. That is, if a handler implements multiple signatures, effect signatures, then it can also just be used for one of them. For an example, that means we have, again, these two effect signatures here for exception and ambiguity, but we also have a third one, which is here called input, and it gives us the capability to read from some ambient input stream, and we get a character back. And using these three effects, we can now implement parsers. And for instance, this is the parser that, given some expected character, we match whether the current character from the input is the same character, and if not, then we raise an exception. And on using this except, we can write simple parsers like this, which reads some number of A's followed by one single B, and also counts the numbers of A in the same moment. So here we see we use these three effects: input, exe, and ambiguity. And in particular, we use ambiguity to model the ambiguity of the grammar. So for the alternatives, we flip here in this case. So since it's just Java programming now, and we're an object-oriented programming language, we can also, instead of having three different interfaces, group these into one interface, which we call P for parser here, and turn this except function now into a method on this interface P. This is now just Java programming. But it has the advantage that we don't have to pass around all these individual capabilities. Instead, this is now the capability that we are using here for reading and here for raising the exception. Same thing for our other parser. We could also make it a method on the P interface, but here we just choose to parameterize it by P, and it's not just a single capability that we have to pass around. It's important to point out that the effect signatures, these three that we have seen, exception and ambiguity and reading from the input stream, they just provide the interface. Okay, so it's still open what's the semantics of the parser. And in particular, since we can capture the delimited continuations, there's many different parsing strategies that we can implement without having to change the concrete parsers or the interface. For instance, we could implement a backtracking parser that just matches or just searches for the very first parse result. But similar to our collect example before, we could also have a parser that enumerates just all possible results. Even more interestingly, we could implement it as a depth first parser, but also as a breadth first parser. That is, we interpret the alternatives of our grammar as different processes, and then the handler itself could be implemented as a scheduler on these processes, implementing a breadth first parsing strategy. And last but not least, we can also implement pull and push based parsers by getting the continuation at that point and having the input stream or some outer process driving the parsing. Again, by the power of the limited continuations that effect handlers give us. The most important aspect is that if we use effect handlers to implement parsers, we can also compose them with other effects. So for instance, if you're implementing a programming language and you're constructing ASTs, sometimes what you want to do is transform the ASTs, like you want to do an A-normal form transformation, which is like let insertion. You want to introduce binders non-locally. This can be understood as an effect and it be implemented as an effect handler. And it naturally just composes with all the other effect handlers and interacts well with backtracking, with the push to pull conversion. So it just interacts very nicely with all the other effects because you use this one uniform framework of effect handlers. So to conclude, I showed you the design of Java Effekt, and in Java Effekt, users have to follow this handler and capability parsing style. They can define their own effects. You can define dynamic effect instances, which is handlers can be created or instantiated at runtime, many different variants. Combining effect handlers with object-oriented programming gives us new modularity and extensibility opportunities. And as we have seen, user programs are just written in direct style. We can use other control flow mechanisms like while and Java native exceptions together with our now new control flow mechanisms. And the performance of our translation is also competitive with existing JVM continuation libraries. There's also a downside right now. These capabilities that we pass down, nothing prevents us from them leaking the handler scope. And this will result in a runtime error. And it's ongoing work to also exclude this, to actually employ effect-safe typing disciplines. With that being said, I'm happy to take your questions. Thank you.
Okay. What happens if there is a built-in exception in some Effekt-related code?
That's a very good question. So our translation, the CPS translation itself, is designed in a way that it interacts well with the native exceptions. So we have this special calling convention where instead of returning from the JVM stack, we return from our own stack. Similar to that, if a native exception is raised, we unwind our separate stack manually until we reach the JVM effect handler, so the built-in effect handler for that particular exception that is raised. So we unwind our separate stack. So
okay.
Hi, thanks for the talk. I wonder if you are aware of this year's ICFP paper capturing future by replaying the past, when they showed that you can actually use exception and state to implement delimited continuations. How does it relate? How your work relates to that one?
Good question. So the question is, how does it relate to a recently presented work at ICFP? In this work that you mentioned, you don't need this bytecode transformation. You can just use exceptions. However, you need to replay all of the, so when you capture your continuation and you want to resume, you replay all of the frames that your continuation contains, and need to redo also all of the computation, which is pure, until you hit the very point where you originally suspended. So this, I assume, I didn't do performance comparisons to this work, but I assume that there might be some completely different performance characteristics.
Thank you.
All right, that's it. So next up.
Thank you.
Next up, we're going to hear from Fabian on empowering union and intersection types with integrated subtypes.